Look at this chart comparing historical face-to-face against fully online completion rates. Online education carries a persistent 10 to 20% deficit in retention. Recently, global events forced rapid expansion, moving institutions beyond just online into a continuum of remote, hybrid, and high-flex models. Faced with this shift, the standard administrative reflex treats the transition as a technology hurdle, solved with intensive learning management system training and software tutorials. But the online efficacy penalty is not caused by a lack of software mastery. The root cause is a systemic pedagogical failure, driven by a deep divide in the academic literature. Mastering digital tools without grounding those tools in cognitive science does not fix the problem. It merely scales bad teaching faster. Modern educational design is governed by two robust bodies of literature that almost never interact with one another. First is the Scholarship of Teaching and Learning, or SOTL, where frontline faculty live. It focuses on cognitive science, prior knowledge, and an active learning climate. But SOTL is heavily biased toward analog environments, lacking actionable tactical strategies for digital-only spaces. The second discipline is Instructional Systems Design, or ISD. This is the domain of educational technologists, focusing on strict outcome alignment, system architecture, and multimedia efficiency. But ISD often lacks the frontline context of student-instructor social dynamics and human empathy. Solving the online efficacy penalty requires bridging these exact domains. Notice the subtitle of this research effort, Merging Instructional Design with Teaching and Learning Research. Synthesizing the empathy of SOTL with the strict architectural rigor of ISD is the only way to build a functional blueprint for digital learning. The first pillar of this synthesized framework requires mapping cognitive architecture directly to digital actions. This matrix shows intended outcomes on the y-axis and teaching strategies on the x-axis. It illustrates a core rule. Different intended learning outcomes require entirely different learning conditions. Let's look at a baseline example, teaching simple verbal information, such as facts or terminology. The cognitive strategy required is straightforward: active, spaced practice paired with immediate, informative feedback. Now contrast that with teaching higher-order rules, like complex problem-solving. This outcome fails via standard video presentations. Complex problem-solving demands authentic tasks, varied problem sets, and phased scaffolding that gradually fades out coaching. The digital tool you choose must serve a precise role here. The software acts merely as the execution mechanism for that required cognitive condition. For example, an automated LMS quiz is not a teaching strategy itself. It is simply the technology used to execute the spaced practice necessary to memorize verbal information. If you do not define the cognitive architecture first, any technology you select will be functionally useless to the student's brain. The second pillar of this synthesis is environmental alignment. It is the strict, unbreakable mapping of an intended outcome to both the learning activity and the final assessment. This flowchart maps ways of learning directly to common methods of assessment. It highlights the most common failure point in digital course design, a severe mismatch between the stated goal and the digital assessment tool used to measure it. Look at this mismatch. If your goal is to teach students how to exercise professional judgment in complex situations, you cannot test that skill with a multiple-choice quiz. ISD literature dictates the correct, aligned method. Professional judgment must be measured through complex scenarios or role play. This alignment forces a specific change in your digital architecture. It requires faculty to utilize virtual realities or branching simulations instead of basic polling software. Strict alignment serves a second purpose. It protects students from cognitive overload by stripping away any digital activity that doesn't directly serve the outcome. In a digital void, brutal alignment is the only guardrail keeping students moving toward a meaningful destination. The final pillar focuses on social and motivational vectors. We have to address the primary psychological driver of the online efficacy penalty: student isolation. Decades of SOTL research prove that interaction is the single highest impact practice for retaining students. Look at this network. The design must establish specific engineered pathways: student-instructor, student-peer, and student-content interaction. You build these pathways digitally using structured, low-stakes formative assessments, collaborative document editing, and peer review tools. Furthermore, Instructors must explicitly build relevance into the material to maintain intrinsic motivation, especially when they are not physically present in the room to gauge the energy of the class. These engineered social vectors serve as the final structural beams connecting the empathy of the classroom with the architecture of the system. An online course without engineered social interaction is not a classroom, it is simply a digital filing cabinet. This brings us to a final underlying question. Does the digital medium change the biological process of how human beings learn? The answer is no. The biological rules of human cognition do not change just because a student logs into a learning management system. This diagram illustrates the proper relationship between teaching methods and digital environments. Notice that as you move across modalities from face-to-face to fully online, the technology load changes dramatically, but the pedagogical bedrock remains absolutely static. When online faculty follow these synthesized pedagogical practices, the performance gap closes. A decade of comparative research from sources like Means and Shachar shows that students in well-designed digital environments can match or slightly exceed the learning gains of a comparable face-to-face course. This occurs because digital models can leverage unique advantages, like asynchronous reflection time and precise automated feedback loops that analog classrooms simply cannot match. To achieve this, we have to stop asking what our educational technology can do and start asking what cognitive condition the outcome demands the technology execute. Excellent teaching is excellent teaching, regardless of the environment. The technology is just the vehicle. Pedagogy must always be the driver.